So let's talk about the transit networking. When it comes to connecting the native VPCs or VNet, the cloud providers will give you this VNet peering, but we discussed that this is not scalable, this is not manageable, because now you are creating a full mesh. You have to create a full mesh because these VPCs are non-transitive. So you are basically increasing the complexity yourself, right? It's very difficult to manage, even for the initial deployment. And just think about updating those routes on regular basis or periodically. It's not manageable at all, I'm telling you. And there is no network correctness. So if someone configured some route somewhere, you don't have a clue what happened and why the network was broken or the routing was broken, right? So yes, it's very difficult, right? So what happens that these cloud providers, they're trying their best to provide you a transit solution. And in AWS case, they support native peering. Everyone supports native peering, that's given. But for the transit, the proper transit, AWS has this AWS TGW. And they came out with this in late November 2018. And you know, AWS has been there for a number of years, like 16, 17 years now. But it's not easy to do the transit, right? It's not easy to do the transit routing or the core routing, and that's why they were so late. And even with this AWS TGW, and there are problems with the visibility. You cannot log into this router. You cannot see the way you want to see it from the enterprise point of view, right? You cannot even peer two TGWs in one region, right? It's a very flat architecture. When you connect VPCs, you configure routes, everyone has started talking to each other. You don't want that, right? And actually, I don't blame them for any of these, because they have to provide this for a lot of thousands of customers. So they cannot provide you all those features, right? So that's the thing. In Azure, we saw that we have a number of options when it comes to transit solution. We have the options to do the transit using the edge router, express route edge router. You can use Azure Firewall, you can use virtual WAN, but we know that everyone actually lacks in one way or another. GCP, they don't even have a transit yet, right? So they want you to use native peering. So they rely heavily on us or vendors like us to provide this transit networking and then transit solution. OCI, same story. They don't have any solution for transit. So customers are using our transit gateways and then our spokes to create this transit network, right? So if you look at the non-Aviatrix third-party transit solution, because obviously there are vendors like Cisco, they have Cisco CSR, and they have vendors like Palo Alto that can actually tell you that yes, you can create the transit solution using our product. But yeah, but then you're managing IPsec, you're managing all those things manually. You're logging into the Cisco CSR, for example, you're creating those IPsec tunnels and managing it. It's not scalable, it's not manageable. And then beyond that, when you're creating those tunnels, because you have to create the tunnel to run the BGP. And when you create the tunnel, it's only 1.25 GB, right? So that's not enterprise grade. And ECMP has issues, it's not supported on the native construct. Its instance size is not in your control, right? So they will dictate you the size because they are bringing the package with them from the on-prem world. The BGP management is your issue, right? Everything is just talking to everyone. There is no policy or security control. So it's a huge blast radius they're creating, right? So a lot of time you end up creating the scripting or Lambda scripts to do even the HA or automation for those third-party provider. So now let's talk about the Aviatrix. So Aviatrix, when we started building our transit solution, we said we have to take an architecture approach, because if the foundation is right, the building that you're building on top will be right? And when you're building even a simple house, you want to make sure that you are not in the flood zone. You are in a good neighborhood, go to school district, all that, right? So the architecture that you're building has to be centrally managed, should provide robust connectivity, should be scalable, scale out. It should give you end-to-end network correctness. It should be encrypted, because, for example, AWS TGW does not provide you encryption, right? And that's, I think, is the biggest reason. A lot of customers, they don't like AWS TGW and they come to our architecture, our transit solution. Inserting the service into the flow is a pain, right? So you need to take care of all that. So this is exactly why Aviatrix is here and solving all those challenges. So this is the slide we saw before. This is how we actually build the slide. Now you have seen the icons, so it will make more sense to you. So in this space, we have this controller. This is the Aviatrix controller, managing the interaction, building this is transit like in minutes, I would say, right? So it's just point and click. And if you're using Terraform, you're just clicking one button and then everything will be done. So yeah, so you create this transit in AWS, and then you repeat it in Azure, and then you repeat it in GCP. So it's so simple and so easy, right? And then when it comes to providing the visibility and monitoring, there are options available within the platform, within the controller. But if you want to go beyond, if you want to provide extreme visibility, then we have this icon which is called Copilot that actually can provide you information beyond what you can get through the NetFlow, through the APIs, through our own internal mechanisms. So I'll just give you one example here because this is important, and this is what a lot of customers are using today, right? So BGP route approval. It's very difficult when you're receiving a route from on-prem and it's coming into your AWS Transit Gateway, for example, or AWS Aviatrix Transit Gateway. What if someone is sending you a wrong route, right? Let's say there is a partner that is connecting to your transit network, and you trust the partner, but it's, at the same time, you don't want him to inject, let's say, default route into your network because it will break everything. So we have this feature which actually allows you to control or approve a route that you receive from on-prem. Okay, so when the new route comes in, the email will go to the admin, and then admin will approve the route, and then it will be injected into the system. So this is just one example of network correctness, and there are examples, a lot of examples like that. For example, TGW audit or Aviatrix Transit Gateway audit, or to make sure that VPC, all the routes are in sync and whatnot. Okay, so I have this link here. This is on the community site. If you search traffic engineering, if you go to community.aviatrix.com and search traffic engineering, I will show you all the different options we have available in the product for you to manipulate the route or do the traffic engineering for your routing domain. Okay, high performance encryption. So when you look at the typical data center or the cloud deployment, you can divide it into different planes, right? So here, what I'm showing in the bottom is physical data center, and on top, this is your cloud, public cloud, right? Now, when you are connecting your public cloud to this data center, as an enterprise, you would like to use service like Direct Connect or Express Route or Cloud Interconnect, because this guy in the middle is not encrypted. This link itself is not encrypted. So you basically trust your own data center for sure. This is your trusted LAN. The public cloud is something you don't trust, but you trust in a way that you're putting your applications there, right? So because they don't provide any data path encryption, but this guy in the middle is of course untrusted. Now, this is Equinix or CenturyLink or Verizon, could be anything. But what about if you want to encrypt this? Right, so when you want to encrypt this link here in the middle, you have an option to create an IPsec tunnel. And when you create the IPsec tunnel, you are limited by 1.25 GB throughput. So that's not good. So you purchase this 10 gig link, you want to encrypt it because this is what your enterprise wants for the compliance or audit reasons, but it's only limited to 1.25 GB. And why is it that? So if you look at the way other vendors or these cloud providers are building the tunnel, they actually use only one CPU core out of this virtual machine or instance. They have no way of utilizing all the cores to build those tunnels. So that's why you see this performance is limited to 1.25 GB. right? And this is true not only when you're connecting cloud to on-prem, but also when you are connecting VPCs together, or even when you're crossing the cloud and connecting clouds together. So that's the limitation they have, right? Now, the way we do it, this is our patented way of doing it. When we build the tunnel or we provide the encryption, we actually utilize all the CPU cores. And that's how we can achieve line rate encrypted throughput. And this is what we call HPE, high performance encryption, or we also call it insane mode. If you go to our docs.aviatrix.com website, search insane mode, and you will see all the documentation for around this. Okay. Yeah, so this is how we actually do it. So we are utilizing all the CPU cores. So now when you look at the cases or the use cases or the problems you are solving for customers, when you're connecting this transit to Spoke VPC, and if you want encryption using third-party mechanism, it's only 1.25 GB, right? Like I said, but in our case, you can go all the way up to 70 gig, which is even greater than AWS TGW, by the way. When you're connecting to on-prem, it's again line rate. So if you have 10 gig, we'll provide 10 gig line rate throughput there, all encrypted. Same thing is true for other clouds. And yeah, for Express Cloud, same thing. When you're connecting the clouds together, you're connecting AWS to Azure, for example, in this case, again, this is line rate. Whatever these guys provide or throttle with, we will honor that and we will give you that line rate performance here. Okay, so that's HPE. Now let's talk about the FQDN egress filtering. So let's take a look at the problem statement here, right? So what happens that when you start building your applications and the virtual machines, pretty much every virtual machine or instance will have this requirement to go out to internet and then pull something, because this is how the modern applications are also written. Okay, so these microservices applications or even the traditional applications, they need to connect to outside world. It could be just a connectivity to a SaaS provider, for example, Office 365, or to OneDrive, or to something else, right? So there is a need to go out there. And then there is a need to go out there to pull some code, for example, to pull things from GitHub, or to pull some patch from the external website. So yeah, so we know that there is a need to go out and pull this thing or connectivity to internet. But if you look at the traditional methods of providing this or solving this problem, is by providing a NAT gateway. So if you go to Amazon, they'll say, okay, deploy a NAT gateway. That's your private subnet, and then you can use NAT. But then when you deploy the NAT gateway, you are only limited to configure rules based on IP, like source, destination, port, and protocol. There is no way for you to write a rule based on a URL or FQDN. And this is exactly the problem we are solving. We are saying that this is not the right way to do it, because oftentimes these services that you're trying to connect to, they keep changing their IP addresses in the background. So how are you going to cope up with those changes, right? It's impossible. Are you going to go back and then add a new IP address or delete an IP address in your NAT gateway? No, this is not how you should do it, right? So when we provide the solution, we give you the option to create the rules or security policies using FQDN. Okay. The service is actually centrally managed, so the controller is managing this this interaction. So you come here, you create the profile, you create the rules, and then you push it to the gateways that you want to have access to internet with using your security posture. And this is actually available both on public subnets or private subnets. This is example from AWS. Right, this is public and private concept is not really valid in Azure, but the idea is same, right? So you can actually create those rules using the simple FQDN. Okay, so that actually will give you the enhanced security towards the egress traffic. And it supports TCP, UDP, HTTP, HTTPS, all type of flows. And you can also create rules like using the wildcard. For example, star.office365.com. I want to allow everything, right? So you can do that. By default, when you create the rule, it's zero trust, so nothing is going out. So you have to create the rules to allow the traffic to go out. That's how we work. Okay. Okay. So these are the two deployment models. So on the right-hand side, you see a distributed model. In this model, the VPCs, each and every VPC will have a Aviatrix gateway deployed in it, which will actually replace the NAT gateway. And then the traffic will go out from here. This is a very popular model because this is how enterprises, they deploy the VPCs. Like every VPC is responsible to go out and then fetch whatever they want to fetch. So you create this whitelist, and then that's how you go out towards the internet. But we have another option to centralize it. So now, as an enterprise, you say, no, this is not my requirement. I want all the internet traffic to go out through this special egress VPC or security VPC. So we can actually also do that. So instead of deploying these gateways in each and every spoke, you deploy it here, you create the policy, you create the rule, and then traffic will go out towards internet. Okay. So we discussed about the egress. What about the ingress? The traffic that is coming in from outside. So what is the problem statement? So if you look at these cloud providers, they actually do provide you some native options for the ingress security. For example, in AWS, there is a feature called GuardDuty. Okay, so this is their threat detection service, but it only detects the threat. So what it does, that it has its own database and their own engine that is checking all the IP addresses on the internet. So if there is any malicious IP address or bad actors sitting out there, they will actually inform you. They will detect it, will say, this is a bad IP, you should do something about it, and that's it, right? It won't take any action. So what we are saying, that that's not good enough. I want to take some action. So what we have a feature for the ingress traffic to do the filtering on the public subnets. And the way it works is that we receive all those findings from GuardDuty. And if there is a bad IP address or bad actor sitting out there, our controller will automatically program the route into the gateway and will block it, right? So you don't have to do anything, right? So we take action on your behalf or on the behalf of this Amazon GuardDuty. So we provide the enforcement, okay? So we pull all this intelligence from the GuardDuty. We automatically, programmatically create these filters or these tables into Aviatrix gateway based on the intelligence or the FQD and egress also, which we discussed previously.